Hey guys, we're Group 18 from SER515. We are here to discuss various software fault tolerance techniques. So let's get right into it. So, what is software fault tolerance technique? It is the ability of a software to detect and recover from any kind of faults. Those are interrupts in our computing terminology, which have happened or are happening in either the software or the hardware, in which a particular software is providing a particular functionality. The software fault tolerance technique is important for building the next generation reliable systems, as the ongoing process should not stop the user's computing experience. This is not a solution to the faults or the interrupts, but very valuable technique to create a reliable next generation system. We are going to go through the three main mechanisms of software fault tolerance. The three main mechanisms are recovery blocks, end version programming, self-checking software. I'll be going through the recovery blocks introduction. So, recovery block mechanism. For simplicity, RCB. RCB was introduced by Horning in 1974 and was further developed by Randall and Heck in the following years. RCB mechanism consists of an executive, an acceptance test, primary, and alternative algorithms. The working of RCB is that when a process enters into the mainframe, a checkpoint is established, then the acceptance test is executed. If that fails, the alternative algorithms are executed until found true. There are n number of alternative algorithms. If one is false, then the control goes to the next, and so on until it is found through. My fellow mate Kaustav is going to explain RCB with an example.
Out recovery block by an example through a code and how it helps us in our programming endeavors. So this is what a recovery block algorithm looks like. It's basically an acceptance test with algorithm 1, algorithm 2, algorithm 3. If the test passes for algorithm 1, will directly go to the truth condition. Otherwise, there will be a test using algorithm 2. Again, if it passes, well and good, true. Else it will go to the algorithm 3. In such way, we can have as many test conditions, as many algorithms as we want. It helps us countering exceptions basically and testing our algorithms. So this was a basic framework which I prepared basically. So I have three search algorithms. One is binary, one is modulo, one is even search, and so we are searching in three different ways. So let me code it up and show it to you. So I'm creating a search algorithm currently, comma x. I've already created the binary searches and all thing. If binary search comma x, if this condition is true, I'll just return a string saying true. Else if it's false, I'll do even search. It actually searches at even indexes for the element x in the list. Return true. Else there is one more algorithm which you can take. It searches at every multiple of 3, at every index which is a multiple of 3, modulo 3 search l comma x, return true. Else the last condition, if all our algorithms fail, I want to return false assumption. So this is a search algorithm. This is an index. Let's put it into practice. I'm gonna search for 3 in. I'm gonna search for 3. Okay, let's search for 3. It's true. Actually, 3 is at the 3 is there in the algorithm. Obviously, I'm gonna search for 11. It's coming true. Search for 1. false assumption. It's not there in this tray. So yeah, that's what recovery blocks are. And Satish will continue with inversion programming.
Hello everyone, my name is Satish. Today I would like to discuss about N-version programming. N-version programming is one of the techniques of software fault tolerance. It was first developed by Avijans and Chen in 1977. Independent development teams uses the same specification to develop multiple versions of the same software. It is based on the principle of design diversity. It uses a concept of decision mechanism to accomplish fault tolerance. By design diversity, I mean to say that teams are independent of each other, they work in a different location altogether. They use different programming languages while building the software, and the algorithm used and the approach to the problem is different. They use different tools while building the software. Even the software development process that is being followed will be different. Inversion programming, as discussed, will use decision mechanism. Decision mechanism will use a concept of majority vote to decide the best result. The versions are run in parallel, and the decision mechanism examines the results and will select the best result if there exists one, else it raises a failure exception. NVP can tolerate both hardware and software faults. The correctness of the N version programming depends on the specification being unambiguous to different development teams. If the specification is ambiguous, the software being built will be different and N version programming will raise a failure exception. This is how the N version programming is structured and operated. Distributed inputs will be the entry point for N version programming. They are passed to the different versions of the software that is being built and the results are gathered. The versions are run in parallel and the gathered results are then passed to the decision mechanism. Decision mechanism uses a concept of majority vote to decide the best result if there exists one. If there exists a result, it will return the result, else it raises an exception. A raised exception will be a failure exception. That means the version built has bugs in it. My friend Raghavendra will continue the discussion on inversion programming. Thank you.
As my friend previously told, I'll be continuing regarding the topic of inversion programming. Now let's see regarding the techniques based on inversion programming. There are four techniques based on NVP. The first one is inversion programming type broker. The next, inversion programming and acceptance test, inversion programming tie broker acceptance test, and the last one comes to N self-checking programming, which is the most commonly used technique based on NVP. Now let's see the advantages of inversion programming. As we know, NVP is based on design diversity technique. It ensures that at least one of the versions will continue to provide the required functionality, and even though the fault arises, we get the required output. The software verification and validation time is reduced as we are executing independent versions in an operating environment concurrently along with the production time. Usage of inversions in VLSI circuits allows the continued use of the chips even with the design faults until the errors at decision point are not similar. Now, let's see the example of inversion programming implementation. The figure shows the inversion programming implementation of software fault tolerance. Here we took the input set of 8, 7, 13, -4, 17 and 44. The functionality is to sort this set of input uh, into the increasing order of the numbers. Here the input set is entered into the NVP. Then the executive performs the following functions. It formats calls to the three versions, and those three calls distributes the inputs to the versions. Each version, that is quick sort, bubble sort, the original incremental sort, are executed separately, and the results of this version executions are gathered by the executor and submitted to the DM. Now the DM examines the result where for every position in the sorted list, it matches with other outputs of each version and verifies whether they are same or not. If the output is same, then it gives the number as the output. And in that way, for each and every position, we'll be calculating the output and we'll be storing it as a result. Now the control is returned to the executive, where the executive passes the correct result outside of the NVP, and the NVP module is exited.
Myself Lakshit. We're gonna discuss about one of the software fault tolerance uh, technique called self-checking programming and its implementations, operations, and an example to discuss in detail. A self-checking program has been implemented in some extremely reliable and safety-critical systems like flight control systems and Airbus A300 and Swedish Railway interlocking systems. A self-checking program uses a program redundancy to check its own behavior during execution. A self-checking program has hardware architecture consisting of four components grouped in two pairs in hot standby redundancy, in which each hardware component supports one software variant. So a self-checking program in a whole consists of two variants, a comparison algorithm, and on comparison algorithm running on each hardware pair. When a self-checking program executes, one of the self-checking component is called an active component and the other components are called spare components. When the active component fails, one of the spare component is switched to for the delivery of the service. When the spare component itself fails, the active component continues to deliver the service as it did before the spare failed. This switching of active component and the spare component is called as a result switching, and it is very important for a safety critical system. To understand the concept of a self-checking program better, we will run through an example or a block diagram of a self-checking program running on a four variants. Here is a self-checking program running on a running variant 1 and variant 2 on hardware pair 1, and variant 3 and variant 4 are executed through a pair 2 concurrently. Now the results of the variant 1 and variant 2 are compared. If they don't match, a flag no match 1 is set indicating a pair failure. Similarly, a variant 3 and variant 4 are compared and the flag no match 2 is set accordingly. If the single pair failure has occurred, the non-failing pair, I repeat, non-failing pair results are returned as a result. If the pair results match either one, the result 1 is equal to result 2 and result 3 equal to result 4, and the results of the pair are compared. If they match, I mean result 1 equal to result 2 equal to result 3 equal to result 4, then the result is set as one of the is set to any of the four matching values and returned as the result of the self-checking program. If these pairs does not match, then an exception is raised indicating a pair failure. Now we will run through an example of a self-checking program. Pramod will run through the example and the issues and discussions related to the self-checking program.
Hello, I'm Pramod. As my friend Dikshit went through the details of N self-checking programming, I'm going to run through an example and I'm going to discuss some issues. In this example, the figure shows us the implementation of an NSCP for fault tolerance. For implementing the NSCP, we need additional components. They are the executive and the comparators. In this example, we are going to sort the numbers 8, 7, 13, minus 4, 17, and 44. So, upon entry to the NSCP, the executive calls all the four variants and distributes the inputs to all the variants, as we can see here. Each variant then starts executing concurrently. Here we can see that the four variants are incremental sort, quick sort, and bubble sort, and heap sort. The results of the variants 1 and 2 are taken and are submitted to this comparator. We can see that the results do not match for both the sorting algorithms. So there is a pair failure and the pairs are not matching. So here we set the flag to no match. And in these two variants, we can see that the outputs are matching here. So there is a pair agreement. And the pair result, as we can see, is minus 4, 7, 8, 13, 17, and 44. So the pair results, the no match flag, and the sorted array are gathered and submitted to the next comparator here. After this, the control returns back to the executive. The executive then passes the correct result, that is the sorted array here, outside the NSCP, and the NSCP module is exited. And some issues with NSCP is NSCP runs only in a multiprocessor environment. The overhead incurred includes additional memory for the second through the nth variance, and also it needs overheads for the executive and comparators. And also, the obvious problem with self-checking software is its lack of rigor, and the code coverage for a fault-tolerant system is also unknown. Without the proper rigor in experiments, I'm sorry, without the proper rigor in experiments, comparing and improving self-checking software cannot be done effectively. And for the architecture for many are discussed before, but from communications between hardware and software, they are generally done through the remote method invocation. And these are the references that we use for our presentation. Thank you.